When you think of snowfall, you might imagine it as simple snowflakes drifting straight down from the sky, soft and gentle, landing in silence. But the truth is that every snowflake's journey to Earth is far more complicated and far more fascinating. Each one is caught in a constant interplay between gravity, air, resistance, turbulence, and collisions. We're going to dive into the physics of falling snow, a story that is part science, part wonder, and entirely unlike the quiet picture we hold in our minds. Let's start with something so basic that most of us never think about it: the weight of a snowflake. A single snowflake is so light that it seems almost without mass at all. Most snowflakes weigh less than 1 milligram. That's 1,000th of a gram. If you collected 100 snowflakes and placed them together, they would weigh less than a single grain of table salt. This extreme lightness is part of what makes snow so captivating. Unlike raindrops, which plummet quickly, snowflakes are constantly being jostled by every little current of air around them. Gravity does pull them downward, of course, but gravity is far from the only force at work. For snowflakes, the atmosphere is not just empty space. It is an ocean of resistance, and they must navigate on their way down. Physics, there is a concept called terminal velocity. It's the maximum speed that a falling object can reach through a fluid, like air. The downward pull of gravity is perfectly balanced by the upward push of drag. For a human skydiver in freefall, terminal velocity might be around 120 miles per hour. Baseball, even faster. But for a snowflake, the speeds are astonishingly slow. Depending on the shape, the thickness, and the amount of branching, a snowflake can drift downward at anywhere between half a mile per hour and 2 miles per hour, and that's slower than most people walk. This means that a snowflake released from a cloud thousands of feet above the ground might take close to an hour to complete its journey. Along the way, it can be lifted, spun, or even pushed sideways for long distances. Scientists have studied snowflakes in controlled environments like wind tunnels, and the results are mesmerizing. Some snowflakes tumble like leaves in autumn, others flutter like fragile paper kites, while still others spin continuously like tiny ice satellites orbiting the air. The beautiful thing is that every one of these patterns is the result of the same principles: the balance of gravity, drag, and shape interacting with moving air. And the air, as it turns out, is never still. Even on the calmest winter day, the atmosphere is alive with turbulence. Invisible eddies and whirls moving through it, and snowflakes get caught in these little rivers of motion. Instead of drifting straight down, they are drawn into spirals, lofted upwards, and then dropped again, tracing out paths that are more like dances than descents. If you ever stood outside in falling snow and watched snowflakes that seem to hover or sway, what you're seeing is turbulence in action. For meteorologists, this makes snow a fascinating but tricky subject. Unlike rain, which falls relatively straight, snowflakes interact with air currents in ways that make their movements unpredictable and endlessly variable. The difference between a gentle snowfall and a blizzard is more than just how many snowflakes are in the air. It's also about how those snowflakes are moving. In calm snowfall, the air acts almost like a conveyor belt, slowly carrying the crystals downward. In a blizzard, rising and sinking currents of air toss snowflakes into total chaos. Some are blown upward so strongly that they never touch the ground. Where they first fell, traveling miles before they finally settle. Others collide midair, clump together, or shatter into fragments that continue their descent as entirely new crystals. What looks like chaos to us is actually an intricate choreography of particles, each one following the rules of physics. One of the most enchanting side effects of snow has nothing to do with the vision at all, but with sound. Have you ever noticed how quiet the world feels after a fresh snowfall? It isn't just you. It's not your imagination. Snow absorbs sound. Newly fallen snow has a porous, lacy structure made up of countless tiny ice crystals, and the air pockets, when sound waves travel into the structure, they scatter and weaken and eventually fade out. Studies show that fresh snow can absorb up to 60% of the ambient noise around us. And that's why a forest after a storm feels so hushed, or why a snowy street seems muted compared to the day before. As the snow compacts and melts, this effect disappears, but in those first hours after a snowfall, the world really does grow quieter. It's physics, creating silence, which may be why we often describe snow as peaceful or serene. Snowflakes don't travel alone. On their way down, they often collide with one another. Sometimes they bounce apart, but often they stick together, forming clusters. This is why you see enormous fluffy snowflakes. What you're really looking at are several smaller snow crystals joined together, drifting as one. On the other hand, collisions can also break snowflakes apart, creating fragments, and then they grow into new ways and they continue to fall in a sense. The snowflake that lands on your glove may not be the same snowflake that began its journey. It has been reshaped, restructured, and redefined by countless interactions with other crystals in the air. So let's get back to the question of speed. It's easy to underestimate how slow snow really is. At 2 miles per hour, a snowflake would take nearly half a minute to travel just 50 feet. That means a snowflake falling from a cloud 1 mile high could remain aloft for nearly an hour, all while swirling in and out of currents, meeting other crystals, changing shape. Compare this to raindrops, which fall at about 20 miles per hour, and you start to appreciate why snow feels so different. Where rain is immediate, snow is lingering. Where rain splashes and runs, snow layers and accumulates. And it's all because of the physics of how a crystal interacts with air. There are also fascinating studies of the shapes that snowflakes take as they fall. Broader, more delicate snowflakes tend to flutter more slowly, while compact crystals like needles or columns can slice through the air more quickly. The branching arms of dendrites act like little parachutes, catching the air and slowing their descent. This is why those feathery, lacy snowflakes seem to drift so gently, while the smaller ones dart. It's a simple case of aerodynamics, the same principles that let airplanes fly and parachutes slow fall also govern the motion of something as small as snowflakes. And beyond the shape, there's temperature. Warmer air near the ground can cause partial melting, which changes the aerodynamics of the snowflake and makes it fall differently. Snowflakes may stick together more easily in warmer, wetter conditions, creating those giant snowflakes you sometimes see in late season. In colder, drier air, the snowflakes remain smaller, crisper, and often more numerous. So the physics of falling snow isn't just about gravity, it's also chemistry, aerodynamics, and weather patterns, all working together in real time. The physics of snow is also why snowfall can be so unpredictable. Forecasting how much snow will accumulate isn't just about knowing how much moisture is in the clouds. It's also about knowing how snowflakes will travel once they begin to fall. Will they clump together and drop quickly? Will they be lifted by strong updrafts and carried miles before touching the ground? Will they shatter and multiply, creating more snowflakes than expected? Meteorologists build these factors into their models, but snow remains one of the hardest forms of precipitation to predict with accuracy. It's a reminder that even with modern science, nature retains its mysteries. So the next time you step outside into falling snow, I invite you to pause and look closely. Watch the way that snowflakes move. Notice the flutter, the spin, the unexpected upward drift. Listen to the way the world grows quieter around you, muffled by the crystals underfoot. Think about the collisions and the clumping, the reshaping that has happened invisibly in the air above. What you are witnessing isn't just winter scenery, it's physics made visible. Every swirl of a snowflake is a dance of gravity and air. Every pause in the silence is sound absorbed by ice. Every giant fluffy snowflake is the story of smaller ones colliding. Snowflakes don't just fall, they tumble, spiral, and glide. They travel paths written by turbulence and resistance, by weight and by shape, by forces too small for us to see, but big enough to shape the landscape. And that is the true wonder of winter. The physics of falling snow is the poetry of motion written in ice, performed over and over again each time the sky opens and lets the snowflakes drift to the earth.